Welcome back to another episode of Gen Ed. We are so excited to have with us Dr. Risto Mikulainen, and he is currently Associate Vice President at Cognizant, which is an IT consulting company. But his roots go back to Finland, where he actually received his master's in applied mathematics and then went to UCLA, where he received his PhD in computer science. As you know, those listening, I am definitely not one for computers. So I am super excited to have someone who knows what he's doing and is actually pretty interesting because he does specialize in neuroevolution and research in that IT field. So, Risto, would you please introduce yourself and give us a little bit of background about who you are besides me just reading off your CV?
Yeah. So I've been doing research my whole life, it seems. Right after grad school, I actually got a professor job at the University of Texas at Austin. And I've been holding on to that, even though I've been for the last 5, 6 years or so, also had one foot in the industry. It became so important and so possible to actually take the technology to the real world. And that's been consuming a lot of my time. University research is great, but it's also mostly focused on fundamentals and basics. And then there are not that many opportunities to actually have an effect and impact in the world, maybe indirectly through your students or through other people who pick up the work. But it became possible in AI and machine learning a few years ago, and I wanted to take that opportunity and actually run with it. So I've been on leave for a couple of years and building applications of the technology that we develop in academia. And also, I found that they are not that far apart, at least today. So my students that are at University of Texas Austin, they may be employed by Cognizant and my research group, and they do their thesis in that group, and they get their degrees, but they also get to use industry resources and get to build applications that they otherwise wouldn't. So that's the current situation. It's all research, but there's a theoretical side and applied side, and there's a industry side and academic side.
Well, that actually partially that leads to one of my first questions, which is, are you more interested in the application of the science that you research, or is it much more theory?
Yeah, it I don't know if I can prefer one or the other. It more or less it's like you go back and forth between them.
Mm.
So there's a time when you develop something very fundamental and basic, and it has its own reward. Just solving hard problems is fun, and you don't really care about anything else. You don't care whether it makes money, whether anybody uses it, or even gets published. Just being able to do something that's hard and solve it. It's like puzzle solving. That's fun. But also, there's an aspect that if you solve something like that, it could open up new possibilities and applications. And like I said previously, it was the case that they were different people who were doing those applications based on perhaps your work, and occasionally you work with them. But now it's also possible to have a much tighter connection with them. And we found that who's better at doing that than yourself? You understand the limitations, you understand the opportunities, but you do have to have collaborators who have different skills, that they actually understand the industry problems or real world problems, because you are not a domain expert. You maybe develop technology that then be applied, but you have to have domain experts that work with on the domain. And currently that is actually my main focus, because I am on leave of absence from UT Austin in order to take some of the technology and build applications in the real world. But even at Cognizant, we occasionally go back and generate fundamental new science, publish papers about it, because there are some really interesting problems that come from real world. Applications are not just something that you build, it's also inspiration. You find some really interesting challenges, and they tend to be interesting also because you know that they matter. They come from the real world, they are difficult, but they also know that if you solve them, there's already something that you can do with it. So in that sense, it goes in both directions, maybe alternates, but you're never that far from either one, at least today in AI.
And would you say that you need to choose between industry work and academic work, or can you balance both? I know you took a leave of absence that you could concentrate more fully on industry work, but before then, did you try and balance both? How did that work out?
Well, it is all research, and it's on my head, and I can't really say that this part of my head goes to academia, this goes to industry. Some of the motivations come from industry, and some of the solutions come from academic interactions, but you are still trying to solve scientific problems. And also, fortunately, today it is possible to have a very tight integration. Like I said, the students who write, say, dissertations, which are very theoretical sometimes and fundamental, they can do that while they are interns, say at Cognizant or some other industry. I had several students who were in other places, Google and other places, for instance. And the IP, the actual technology that can be commercialized, is already commercialized in the industry. But the academic credit, getting a dissertation, for instance, or master's thesis or something done, that can come through the university. And also the industry can pay for the students' salary and in that sense support them. Previously, it was only possible to support students through research grants from federal sources mostly. And now it's possible to support them through industry sources. But I have to say that this is relatively new. And I think also, at least in several cases that I've been watching closely or been part of, it's been very productive. And hopefully this is something that's available in the future, that academia industry are quite close. And the industry folks, they publish in the same conferences. They are part of the same academic community, research community. So you can do research now in academia and industry and in one and the same community. And I think that's really wonderful. We are having a really great time that way. There are many more career paths now than there used to exist for people who want to do research.
Definitely. So, could you explain a little bit about like your day in a life as a researcher, as someone in the industry, and maybe compare it to what it was like while you were teaching at university, and what research are you currently working on? I know that's a lot of questions.
Yeah, that's a lot of questions, and all of them are pretty big. So being on leave means that I don't teach classes, and that's one of the bigger aspects of being an academic, being a professor, is the classroom teaching. And there's a role for that. Of course, it's a end of itself. It's really useful to train the future generation of experts and researchers. But also, it's a source of interactions and ideas. For instance, in teaching undergraduates, I enjoy the part where undergraduates are fearless. They don't have to think about where their next grant is coming from or whether they get paper published. They can tackle any problem. They don't know that it's impossible to solve it. So they have so much energy and so much enthusiasm, and that's really quite inspiring. And grad students, on the other hand, they're already starting to become experts. They know quite a bit. They follow the literature, and I often learn from them because I don't have time to follow everything, but they can explain it to me even though I didn't have a chance to become an expert myself. So they become more colleagues. Like postdocs, then the highest tier, they are much more colleagues. They already have a PhD and they are pulling their own projects and so on. So even from the classroom, you get a lot of research ideas. You also train the people that you will work with and hopefully become leaders in the future. But a big part of teaching is also teaching individual people in individual projects. Some of them are undergraduate projects. They just want to try out on their own whether they can make something worthwhile, all the way to, like I said, grad students and postdocs who do projects that turn into dissertations and eventually perhaps even applications. So that part still stays there. Even if I'm on leave, I have to take care of my students and work with students and postdocs. The classroom teaching is the part that you get a relief from, and that time you can use on doing research, for instance. But you can't stay away too long. I mean, you get to know the people because you teach them in a classroom, and you recruit students from there, and you find the people to work with in independent projects. And it's also a way of staying current. So that's why in academia you can stay away for about a year, maybe 2 years, but then you come back and become a full-time academic again. That's usually the plan. I don't know how many questions that answered. One and a half.
That answered quite a few.
Yes.
Now, your particular interests lie in evolutionary computation and neural networks. Just for our listeners out there, for the layperson who doesn't know that much about these topics, how would you describe them?
So both of those are part of a general framework of artificial intelligence. And within artificial intelligence, machine learning, it's not necessarily a hierarchical relationship, but there are other types of artificial intelligence systems that don't learn necessarily. They may be programmed, for instance. But in machine learning, evolutionary computation and neural networks are two different aspects of it. Neural networks typically are learning machines, statistical learning machines that learn from a massive amount of data. And that might mean like 100 million examples of images, for instance, and learning to classify them to different categories. So recognize images, recognize faces, for instance, or objects, or maybe diagnosing diseases. I mean, for all of those, you might have a data set where there's a problem, an input, and then there's a label of what kind of input that is. And that's what the neural network is trying to learn. It's learning this mapping from inputs to outputs that some humans already have labeled. Most of the time they are humans. There are some automated ways of doing that. For instance, weather prediction can be automated because you know what happened in the weather next day. So you can learn to make a prediction of what happens even without actual human labeling. But that's what the neural networks typically learn. They learn this mapping based on data set where you know what the right answer is. And that's useful. I mean, you can take a computer vision to a car or something else, that robot, and it can recognize situations in the visual world that they've never seen before. Or you can imagine how useful an automated diagnosis might be. You have a new patient and with new kinds of symptoms, but the neural network has seen many similar cases before, so it can statistically match it with previous experience and make a good diagnosis. And in many such cases, these neural networks can already do better than people. And we have several examples in our own lab too. And that is actually starting to be useful. If you can beat a person in recognizing, say, categorizing images, or maybe doing a diagnosis or estimating somebody's age or whatever it is, that can be a good source for applications. So that's what neural networks typically are. Evolutionary computation is a little different in that the idea there is that you don't already know what the right answer is, but you are trying to create it. You're trying to create something that optimizes a task, does as well as possible when you don't know what the right answers are. So it might be, for instance, game playing. We don't know what optimal way of playing chess is, or playing tennis for that matter, or many other tasks. We don't know the actual actions you should perform at any one time, but you can tell how well you do over time. And that kind of a feedback, not exactly that there's no teacher telling you what to do, but there's an evaluator telling you how well you're doing. And using that feedback of how well you're doing, you can explore, you can try out different things and try to find actions or policy of actions, different, like a mapping from inputs now to actions that maximizes this kind of a signal, evaluation, fitness or reinforcement, it's sometimes called. So in that sense, it's very different. It's a search mechanism. It's not a mechanism that tries to fit the data into a very big nonlinear statistical model and therefore be able to do well in similar situations in the future. Evolutionary computation is a system that searches for good policies of actions, good behaviors, even when you don't know what you're doing necessarily, what the good answers are. And there again, we can do better than people. We can learn to play games better than humans. We have many examples of that as well. Designing websites, for instance, so that they are more effective in engaging a person. Or maybe coming up with recipes for agriculture that grow plants that are maybe tastier or bigger or grow faster. And we can exceed capacity of humans to come up with these designs. And I think that is really fascinating. Most of the AI up to now has been on supervised learning, the neural network type of AI, modeling, predicting what we already know. And I think in the future, we can invoke AI in roles where they are creative and they create solutions that we don't already know. And I think that is really exciting. We can make the world better by using AI to create things that we don't quite know how to do.
Now, these two research domains seem somewhat at odds with each other. Do you ever use them conjointly? Or at the moment, are they completely separate?
No, there's many ways of using them jointly. You can, for instance, use evolutionary computation to evolve neural networks. And neural network is then the policy, the strategy. It expresses your behavior. And that's perfectly fine. It's just that it was constructed using an evolutionary search instead of training with examples where you know what the correct outputs are. So you can use neural networks in that role as well. Things get very confusing if I start talking about all the different ways that they can be combined. But there's another way that I should mention, and that is when you are actually trying to find a good policy or behavior, but it's in a domain where it's very difficult to evaluate how well you're doing. So, for instance, in recommending treatments, you don't want to experiment with patients. You don't want to just try some new ideas when you have a real patient. So there, we first train a neural network using supervised learning. That's very standard to serve as a surrogate model for the world. So now we have it's imitating the world. It's like a digital twin of the world. And now we can ask, well, if I have this kind of a solution, how good is it? And you ask a neural network. A neural network can give you an estimate because you trained it to emulate the world. And that's a really nice combination of supervised learning, neural networks, and evolutionary search. You use the supervised learning as a surrogate so that you can search more efficiently. So, for instance, in that application where we tried to discover good growth recipes for agriculture, we only had a chance to implement or plant about 200 different plants. They were basil plants, and watch them grow and measure them. It takes 3 weeks for them to grow. So we only had enough time for a few hundred. But with the surrogate model, we could test millions of different growth recipes and find those that might work better before we actually ever implemented them. So this is a way of making it possible to search for good solutions in domains where it's costly or dangerous or unethical to experiment in the real world.
So
That's
it's
amazing.
basically AI playing off of another form of AI to mutually improve each other.
Yes, that's exactly what it is. And in the first case where I was saying that you evolve the neural network, it's AI designing AI. So that's where it gets complex.
That's a crazy concept.
That's really interesting. And so this leads on to my next question, which is, we know that you got your MS in applied mathematics. How did you get into evolutionary computation and neural networks? How did you move from applied mathematics to computer science and specializing even further?
Yeah, I'm not sure if I ever moved. It's just that you do get excited about different opportunities at different stages in your career, and it's always been the same kind of motivation, trying to build something that does better than we can do today. So in mathematics, well, I wasn't a pure mathematician ever really, and that might be a little different if you really just develop in mathematics, but it was more applied. So we were doing optimization, linear optimization, nonlinear, and dynamic optimization. Those are it's a branch of mathematics, applied mathematics. And then finding that neural networks could be applied to some of the same tasks, and especially evolutionary optimization could be applied to some of the same tasks. And it seemed to me that there was more power, and it was new and exciting, of course, but there was a power in that neural networks and evolutionary computation could deal with situations that are nonlinear and very high dimensional. So scaling up. The mathematical methods are very powerful, but they often have many constraints before you can apply them. You have to do a lot of simplification, linearize the world, and simplify the relationships and rule out a lot of variables. And these techniques of AI type of techniques, and evolutionary computation in particular, it allows you to scale up. We can have problems with a billion variables, versus humans can deal with 7 plus minus 2, and other techniques maybe 10, 15 variables. So we can really scale it up by orders and orders of magnitude, and similarly find solutions in very large search spaces with nonlinear relationships. So that was the motivation. I really wanted, first of all, do something new, but also something that would scale up and would be possible to take the real world without having to do a lot of work in trying to cheat and simplify. It's not cheating, it's simplifying, and it can be really useful. And I'm not knocking it, but the point is that you can do more potentially, and that's what really keeps you going. It's the promise. It's like, maybe this will work. Let's see if this will work. It could really change the world if it did. So that's excitement came along with these new techniques, and I'm totally still on that trajectory.
So would you say that your interest in research came from this ideal of changing the world, of making a concrete impact?
Well, there are many motivations. And like I said, part of that is that it is very satisfying and fun to solve problems that you have. Just puzzle solving itself is. And when you can do that, that's even pure mathematics has that too. That you have a very high satisfaction by solving something that is difficult, and people think that you're smart because you solve hard problems. Yeah, that's part of the motivation. It's a challenge, and that's why people like puzzles in general and games. So there's that aspect of it. But it's true that in science, it's not always, you don't always have an impact. And we have a little bit of a nagging doubt that we are doing papers that are write only. We write papers, but nobody reads them. Nobody, runs with them. And at one point, having done a lot of papers, I really wanted to make sure that some of that has an impact. So that became a big motivation. And it also has to do with your career, where initially you want to demonstrate to everybody that you're smart. That's how you get your job, and that's how you get students. That's how you get all these resources. But towards later in your career, you want to have an impact. You want to leave a legacy. So you actually want to do something that probably has a lasting impact on its own. And one way to do that is to take the technology to the real world. And that's been a big motivation, yeah.
So which one of your projects or previous research experiences have you felt will get that impact out?
And that's also very hard to tell. I mean, in science, especially when you're doing fundamental, sometimes decades later, things are picked up and found to be useful. And that's happened over and over and over again. And also in this current AI excitement, that's exactly what happened. A lot of these ideas that now work were invented in the 90s, 20 years earlier or more. And they are now becoming actually useful. So you got to believe that what you're doing is useful at some point, but maybe it is that you don't quite have the resources. So, for instance, the evolutionary computation is right on the cusp of having enough resources so that it can do this kind of discovery and create problem solving that's useful. And before it becomes widespread, we may actually have to have more different kinds of computers. Now, in the past, we did a couple of things that I thought were quite interesting. We did a visual cortex modeling, and that was actually the point. There was not so much building applications, but it was understanding the fundamentals of processing in the visual cortex. So brain, like it was actually modeling neurons in the brain and structures in the brain. So that there the focus was basic science, neuroscience, and building a computational understanding of it. And that's a kind of contribution that might actually have a lasting impact that much later, because we were not building an application for that time. We were building a foundation for computational understanding of the brain. And we continued that, and now we have actually a project where we are constructing neural networks that are models of individual patients who had a stroke and they had language trouble. They are bilingual, they lose one language or another, different dimensions, different amounts. And we are building a model of each patient separately, and then we test different treatments on that model, and then make recommendations of how this particular patient should be treated. And we've progressed so far that this is actually in a clinical trial now, in an actual NIH approved clinical trial, being evaluated whether it helps real people, real patients. So this has been, I think, a wonderful step that you really try to take this to the real world, to helping people who've had an injury of some kind. And in that sense, I'm hoping that it could be really instrumental in the future and impactful. As far as we know, this is the first time that anybody's built an artificial neural network as a model of an individual real neural network in order to help come up with better treatment. So that's
Well, congratulations. That's a big
the trial is underway. We haven't finished. They will be finished in a year or so. We'll see. But in any case, this opportunity, I think, is great. It also paves way for many others to do something similar. So one that's currently in my mind is this system that we talked about, where you are building a surrogate of the world, and then you are optimizing how you deal with the world. So we built a model of actually COVID-19 and the interventions that governments can enact in order to contain and mitigate the pandemic. So things like whether you should close the schools or ask people to wear masks, require them to wear masks, all kinds of things, transportation, international travel, workplace restrictions. There are many different dimensions that have been tried in various parts of the world. And of course, we have the data almost real time coming out, how the case numbers and hospitalizations and deaths progress. And we built a surrogate model of how these interactions actually affect the progress of the pandemic. And then we used this evolutionary search to come up with optimized recommendations. And this is actually, I think, really exciting. It is currently a demo, and you can actually go and see it. I mean, you can interact with it. You can even go back in time and see if you could have done better. And it's in evolution.ml. You can find it under there, and it's interactive. And it was built as a demo, and we're in the process of analyzing all these aspects of what actually matters. And the point is that hopefully in the future, this technology can be useful. There might be another pandemic. There might be other challenges, forest fires, hunger, climate change, where governments and decision makers have to decide on a course of action in order to achieve something as a society. And we believe that this kind of technology could be really helpful in that if we can build this, first of all, we have to agree what we want. You know, that can be difficult, and I can't really help with that. But as a society, we need to decide whether we want to maximize productivity, equality, protection of environment. There are many different values like that we have to agree upon. But once we have agreed at that, we can use AI to come up with strategies and policies that get us there. And we can get there without various issues that come in the way in a real society, like people have different opinions, pet peeves, they have, well, in Bat's case, there might be graft, there might be pork, all kinds of things that get in the way of implementing and finding what needs to be done. So we can use AI to make optimal, objective decisions, as long as we agree what we want. So for the first time, we can make the society what we want using AI in that role. So that's a big picture. And if I leave a legacy, I really hope that will be that one, because that has a very broad implications.
Incredibly broad. What's the name of the demo again? It's Evolution.
Okay, the website that's in a Cognizant, our
Yes.
Cognizant AI Labs, is evolution.ml. And underneath that, it's pretty easy to find this demo. It's in demos/NPI dashboard, non-pharmaceutical interventions dashboard, one word.
All right.
So it's easy to find, and you can indeed interact with it. That's what makes it fun. And we also added ways of coming up with your own designs, not just looking at what the AI recommends, but you can modify them. And you can also go back in time, like I said, and look at alternatives that way and compare what actually happened. So it's a pretty powerful demo.
We'll be sure to link it down in the description of this episode so that all our listeners can go interact with it themselves and experience the power of AI and the potential of change that could bring to society.
Yes, this has enlightened me to see AI in a new way versus those in like the robots taking over the world and like the movie type things. So thank you for changing my perspective and giving a really positive outlook, I think, on what can be for AI and IT in general.
Mm-hmm.
So as this episode is coming to a close, I want to thank you again, Risto, for coming on and sharing your passion for this topic.
Yes, thank you very much.
Yes, my pleasure. Thank you.
All right. Well, we'll see all of you next time on our next episode of Gen Ed. See you then. Bye-bye.